Finally, in the third part of this talk, I'd like to mention some examples of 7 manifolds with G2 holonomy, and I'd also like to mention some interactions that G2 geometry enjoys with both calibrated geometry and, briefly, gauge theory. The discussion here is going to be very, very brief. I'm not going to give any details. The idea is just to give a sense of some of the questions that are being asked and give a sense as to the flavor of the subject as it currently stands. So recall that our strategy for constructing metrics with holonomy equal to G2 goes like this. First, what you'd like to do is construct a torsion-free G2 structure. That means solving the first-order PDE system, d phi equals 0 and d star phi equals 0. This appears to be a linear system. However, it isn't, because remember, the Hodge star depends non-linearly on phi. If you do this, if you solve the system and get a torsion-free G2 structure, then the induced metric will have holonomy contained in G2. And then the second step is you can apply either Bryant's criterion or Joyce's criterion. Okay, step one is not easy. It's a very non-trivial thing to do. And as far as I can tell, most examples use one of the following ideas. One idea is 7 equals 6 plus 1. The idea being that you would build your 7 manifold from a Calabi-Yau threefold, that's a real dimension 6, or a nearly Kähler 6 manifold. And the other idea is that 7 is 4 plus 3. So you somehow build your 7 manifold from 4-dimensional and 3-dimensional pieces. So the first existence theorem at all for metrics with holonomy G2 is due to Robert Bryant in 1987, who wrote a very foundational paper that introduced a lot of the ideas in the subject that are still being used. And so the existence theorem goes like this. On small balls in R7, there do exist G2 holonomy metrics. In fact, there exist lots of them. The generic metric depends on 6 arbitrary functions of 6 variables in the sense of exterior differential systems up to diffeomorphism. So what does this mean, depends on 6 arbitrary functions of 6 variables in the sense of EDS? What this means is that you can construct a generic metric with holonomy G2 by solving a system of Cauchy problems. And the initial data that you can freely determine or freely specify in your Cauchy problems is 6 arbitrary functions of 6 variables. Okay, so the way this was proven is via the Cartan-Kähler theorem. I'm stating this very loosely. One needs, for example, the assumption of real analyticity, but no matter. He also, in that paper, constructed the first explicit example of a metric with holonomy equal to G2. So this is somehow very concrete and down to earth. So consider the 6-manifold SU3 mod T2. This is a compact 6-manifold, and you can equip F with a certain homogeneous metric that I won't explain, but this is the homogeneous nearly Kähler metric. This is in particular an Einstein metric of positive scalar curvature. Not the only Einstein metric, but it's one of them. Then what you can do is form the cone over this 6-manifold. So this is somehow 7 equals 6 plus 1 for you. You form the cone over this 6-manifold, which is just R plus times the manifold, and you equip it with the cone metric. And Bryant shows that you can get a torsion-free G2 structure out of this. It has holonomy contained in G2. This is the induced metric. And in fact, you get holonomy equal to G2. This construction was in fact generalized later by Baer in '92, who realized this is an example of a more general phenomenon. So in general, if you have a Riemannian 6-manifold other than the round 6 sphere, then call it X, then X is so-called nearly Kähler, if and only if its cone has holonomy equal to G2. So this gives you a way, in principle, of constructing lots of cones with holonomy equal to G2. And cones are important, for example, as models of, well, conical singularities. So this is something you'd really like to have a lot of. Unfortunately, it turns out that nearly Kähler 6-manifolds, or at least compact ones, are very rare. They're very, actually, compact nearly Kähler 6-manifolds are quite hard to find. At present, there are only 6 known examples of compact, simply connected, nearly Kähler 6-manifolds. So 4 of these have been known for a long time. These are homogeneous spaces. There's the 6-sphere, S3 cross S3, CP3, and F6 from the previous slide. Here I should point out that although S6 has the round metric, CP3 does not have the usual sort of integrable complex structure. Here we're thinking of CP3 as equipped with a non-integrable complex structure, so this is not the Fubini-Studi metric, and S3 cross S3 is equipped with a certain homogeneous metric that is not the product metric. So just keep that in mind. And so these are in fact all of the homogeneous nearly Kähler, compact homogeneous nearly Kähler 6 manifolds, and so you'd like to find more. And relatively recently, Foscolo and Haskins, in a very beautiful paper, succeeded in constructing 2 more. So they found some exotic metrics on the 6-sphere, and or 1 exotic metric on the 6-sphere and 1 on S3 cross S3, both of which give nearly Kähler structures and hence and that are cohomogeneity 1. And so these are sort of the 6 minus 1 is 5 examples that we now have of G2 holonomy cones where the link, the cross-section, is compact and simply connected. So far we've only discussed incomplete examples, but in fact there are examples of complete metrics with holonomy equal to G2. We now have quite a lot, but the first known examples were due to Bryant and Salomon. These are the so-called Bryant-Salomon manifolds. They found 3 examples, each of which carries a 1-parameter family. And their examples are the total spaces of vector bundles. So this is sort of the 7 equals 4 plus 3 idea. So the vector bundles they use are lambda 2 plus, this is the space of self-dual 2 forms on the 4-sphere, lambda 2 plus of CP2. Both of these are rank 3 vector bundles over Einstein 4 manifolds. And they also consider the spinor bundle of S3, which is a rank 4 bundle over the 3-sphere. Okay. So on each of these vector bundles, they construct a 1-parameter family of complete metrics with holonomy equal to G2. In fact, there are some quite interesting geometric features of their construction. So for one thing, all of their metrics are sort of bundle metrics. They use this ansatz to get very explicit examples. They sort of assume from the outset that their metric has this very simple form, okay, where here, again, pi is the projection, and alpha is some quadratic form that restricts to the flat metric on the fibers. And if you assume that your metric has this form, you can write down the corresponding G2 structure, and then the closed and co-closed condition reduced to a system of ODEs, which they can actually solve explicitly, which is quite beautiful. So in other words, as you might suspect, these metrics have a high degree of symmetry. These are all cohomogeneity 1. In fact, they are also somehow can be viewed as 7 equals 6 plus 1 at infinity. If you look out at infinity and sort of very far in the fibers, these are all asymptotic to G2 holonomy cones, right, on the previous slide, the homogeneous ones. So these are all examples of asymptotically conical G2 metrics. Okay, so something much more difficult to do is to construct compact examples. And the idea of constructing compact manifolds with G2 holonomy is the following. Here's the idea. What you'd like to do is is to take a compact 7 manifold and construct a G2 structure that is close to torsion-free in the sense that it's closed and close to co-closed. So D star phi is small in some sense that I'll make precise in a second. If you have such a thing, then maybe you could perturb your G2 structure to a new one that is actually torsion-free. So this is the idea. So to make this a little more precise, let's say an almost G2 structure on a 7 manifold is a pair phi, which is and psi, where phi is a close G2 structure and psi is a 3-form that is in some sense a first integral. So d star phi equals d star psi. And so the relevance of this is a very powerful theorem of Dominic Joyce. This is basically the main tool that we have for constructing compact 7-manifolds with holonomy equal to G2, and it's based on the idea mentioned at the top of the slide. So here's the precise statement. Let's say you fix constants a1, a2, a3 positive. Then there exists an interval 0, t with capital T positive and also a constant k positive such that the following is true. If you have any compact 7-manifold that comes with a 1-parameter family of that should be almost G2 structures, satisfying the following 3 sets of estimates, then in fact your 7-manifold admits a 1-parameter family of torsion-free G2 structures that are close to the closed G2 structures that you started with. Okay, so they're close in the sense that this estimate holds. And in fact, they can be taken to be in the same cohomology class. So the idea basically is that as t goes to 0, you should imagine that these G2 structures kind of degenerate. But they don't degenerate too badly. That's basically what B and C say. So even if the structures degenerate so that the injectivity radius goes to 0 and the curvature blows up, somehow the rate at which the injectivity radius goes to 0 and the rate at which the curvature blows up is controlled. Okay, and on the other hand, at the same time, d star phi is getting smaller and smaller and smaller. That's what's explained by A, essentially. And again, the rate at which d star phi is going to 0 is also controlled. Okay, I should point out that actually satisfying the hypotheses of this theorem is non-trivial. Right? It's not easy to find inputs to feed into this theorem. And this is partly because just simply finding compact 7-manifolds with closed G2 structures is quite hard. And then, of course, finding ones that are closed G2 structures with d star phi small is somehow even harder. But it's not impossible. This has been done. The original example was done by Joyce, who drew inspiration from the Kummer construction of K3 surfaces. And so Joyce's original construction was somehow sort of a G2 analog of the Kummer construction in the theory of K3 surfaces. A different construction was suggested by Simon Donaldson and carried out by Alexei Kovalev, and this is called the twisted connected sum construction. And this was then clarified and significantly strengthened by Corti, Haskins, Nordstrom, and Pacini. And the result is that we now have tens of thousands, if not maybe millions, of compact 7-manifolds with G2 holonomy, sort of all sorts of topologies. It's really quite amazing. And recently, there's been a construction due to Joyce and Karijanis, which in some sense is similar to the G2 Kummer construction, though there are also some important differences. I should mention that all of these constructions are geometric gluing constructions, right? So they involve some very delicate geometric analysis. They also draw inspiration, all of these draw inspiration from the theory of Calabi-Yau manifolds, sometimes very directly. So what this means is that somehow progress in G2 geometry is often dependent on progress in Calabi-Yau geometry. In particular, the theory of Calabi-Yau threefolds has played a very important role in the theory of compact 7-manifolds with G2 holonomy. But still, many open questions remain. So, for example, at the moment, our method for constructing torsion-free G2 structures comes from starting with a 7-manifold with a closed G2 structure. And actually, not only is it hard to find 7-manifolds with closed G2 structures, the following question is open. If you have a compact 7-manifold that admits closed G2 structures, does it necessarily admit a torsion-free G2 structure? This is unknown. In particular, it's not known whether the 7-sphere admits a closed G2 structure. It definitely can't admit a torsion-free G2 structure for topological reasons, some of the obstructions I mentioned earlier, but we don't know whether it admits a closed G2 structure. So this is somehow related to the previous question. Moreover, now that we have tens of thousands, if not millions, of compact 7-manifolds with G2 holonomy, we have the interesting question of how do you tell them apart? How can we distinguish G2 holonomy 7 manifolds from one another? In other words, what you'd like is some sort of invariant of G2 manifolds. Okay. So on that note, I'd like to mention some connections that the theory of special holonomy, or G2 geometry in particular, enjoys with two other areas of mathematics, geometric analysis, namely calibrated geometry and gauge theory. There has emerged in the subject this wonderful trinity of these three subjects of special holonomy metrics, calibrated submanifolds, and gauge theoretic objects on them. The link between calibrated geometry and gauge theory is a very fascinating one that is sort of very unclear. One often thinks of calibrated geometry as somehow dual to gauge theory in a way, but maybe making this precise is sort of an open question in research. So I'm being very vague, so maybe I should bring this discussion a little more down to earth. So this is going to be a extremely rapid introduction to some of the ideas in calibrated geometry. So a calibration on a Riemannian manifold, just in general, just any Riemannian n manifold, is a differential k-form that satisfies two properties. So first, a calibration has to be closed, and second, it has to have comass 1. Okay, and what that means is that if you plug in an oriented orthonormal basis, you have to get something that's at most 1. And one more piece of terminology, let's say that an oriented submanifold of dimension k is calibrated by your k form if you get equality here on the tangent spaces of sigma. Okay, and the reason why these definitions are interesting is that this is somehow rigged to satisfy this theorem. So this definition is due to Harvey and Lawson, and this observation is due to Harvey and Lawson, which goes like this. Let's say you have a Riemannian n manifold, and alpha is a calibration, say a k-form, and you have an oriented k-dimensional submanifold. Then your submanifold, if your submanifold is calibrated by alpha, then it is volume minimizing in its homology class, meaning that its volume is less than or equal to any other competitor in the same homology class. Submanifolds that are volume minimizing in their homology class are extremely rare. This is a very rare and beautiful property for a submanifold to satisfy. As far as I know, all of the examples we have of this sort are calibrated. The classic examples, of course, are the complex submanifolds in Kähler geometry, but we now have plenty more thanks to Harvey and Lawson's work. Note that this condition is much stronger than being minimal, right? Certainly minimal submanifolds need not be volume minimizing in their homology class, but volume minimizers are certainly, it's a very strong type of minimality. Okay, so calibrations are obviously a very great thing to have, so where can we get our hands on some? How can we get calibrations? And it's a beautiful fact that manifolds with special holonomy carry natural parallel calibrations. Okay, so the classic example again is in Kähler geometry. The Kähler form is a calibration. And in fact, its normalized powers, 1 over k factorial times omega wedge itself k times, these are all calibrations. And their calibrated submanifolds are precisely the complex submanifolds. So in other words, complex submanifolds are volume minimizers in their homology class. And that observation was in fact the inspiration for the definition of calibration and for Harvey and Lawson's work. And sort of an example of taking a theorem and turning it into a definition. But I just want to comment briefly on the case of interest to this talk, which is the case of G2 holonomy. In the case of holonomy G2, or even contained in G2, the three-form phi that defines the G2 structure, as well as its Hodge dual, both of those are calibrations. So let me say that more formally. If you have a seven manifold with a G2 structure, phi, as long as phi is closed, right, that's the first part, then phi is a calibration, meaning that phi always has comass 1. The three-dimensional submanifolds that phi calibrates are called the associative threefolds. Okay, so say that a submanifold sigma 3 is associative if it's calibrated by phi. Okay, this is equivalent, it turns out, to saying that the tangent spaces are closed under the operation of the vector cross product. Okay, so if you have two vectors in the tangent space, then their cross product is 2. And you might ask, where does the name associative come from? Why are these things called associative? Again, it's because an equivalent condition is that each tangent space has a basis that associates. Remember that octonionic multiplication is not necessarily associative, but on these tangent spaces, it is. Okay. And these properties are somehow reminiscent of the characterizing features of holomorphic curves in complex geometry, and I'll say more about that in a minute. But right now, I just want to point out that the Hodge dual, the 4 form, is also a calibration provided that it's closed. And again, you might ask, is there anything interesting about the submanifolds that it calibrates? So those submanifolds are called coassociative. So say that a 4-manifold is coassociative if it's calibrated by the 4 form, star phi, meaning that the 4 form restricts to n to be the volume form. Okay, an equivalent condition is that the 3 form vanishes on n, and another equivalent condition is that if you take 2 vectors in n, then their cross product has to actually be orthogonal to n. Here I'm speaking a little imprecisely. I'm kind of ignoring issues having to do with the orientation of the submanifold. Probably point 3 should say phi restricts to n equals 0 and n has the appropriate orientation, but I'm being a little sort of careless with this point. So how should we think about these? There's an analogy that's been very influential in the subject. It goes like this. If you think of torsion-free G2 structures as somehow analogous to as 7-dimensional analogs of Calabi-Yau manifolds, then we can think of associatives as somehow the G2 versions of holomorphic curves. And we can think of coassociatives as the analogs of special Lagrangians. This analogy is, again, not perfect, but it's a surprisingly good one, and it has motivated a lot of work in this area. Now, in symplectic geometry, one can talk about the Gromov-Witten invariants. These are invariants of a symplectic manifold obtained by counting the holomorphic curves. So if one believes this analogy, one might ask whether moduli spaces of associatives might also be used to obtain invariants of G2 manifolds. So this is a line of reasoning that's under investigation by several people. There are many difficulties to making this work. But still, there's, I think, a lot of hope that somehow this might be done, that one can obtain invariance of a G2 manifold by counting associatives, meaning by deriving information from the moduli space of associative threefolds. And finally, I won't spend really any time on this, but dual to submanifolds are gauge theoretic objects. And there are now, these days, several different types of gauge theories one can pursue and study on 7 manifolds with various kinds of G2 structures. So one can study G2 instantons, monopoles, deformed G2 instantons. These are somehow analogs, well, the first one is an analog of the anti-self dual connections that play a prominent role in 4-dimensional geometry and topology. And so, one hopes that maybe similar types of objects and moduli spaces might play a similar role in the 7-dimensional theory. So in that direction, Donaldson and Thomas noticed sort of some analogies between G2 instantons on 7 manifolds, although they drew a connection relationship with an analogy with flat connections on 3 manifolds. And they asked the question of whether G2 instantons might give an invariant of G2 manifolds. This turns out to be a tricky thing, in part because Tien showed in a very important paper that sequences of G2 instantons may bubble along, so they degenerate in a certain way along associative threefolds. And this means that compactifying the moduli space of G2 instantons is going to be a very difficult thing to do. So in light of that, there was sort of a kind of an updated program that was proposed. And so perhaps what one should do is count G2 instantons, but one also has to take into account, the associatives that also exist in the G2 manifold, and somehow some sort of weighted count might produce an invariant of G2 manifolds. This is a very large project. A bunch of people have worked on this. I apologize for missing people. There's a lot of very exciting work that's been done, but there's certainly a lot more to do in making this program work. So hopefully this whets your appetite for more G2 geometry, and I didn't mention anything about its cousin, spin 7 geometry in dimension 8. There's sort of very similar stories there. And hopefully this inspires you to learn more about this wonderful and exciting area of differential geometry and geometric analysis. Well, thanks again for the invitation, and thank you all for your attention.